Hi everyone, my name is Yoni, and in this video I'll present our paper, Concept-Guided Fine-Tuning. Let's start with the problem. Despite impressive accuracy on standard benchmarks, modern vision transformers are surprisingly fragile when the world looks a little different from their training data. The root cause is spurious correlations. Models often achieve high accuracy not by understanding objects, but by latching onto background textures and contextual cues that happen to co-occur with a class during training. Look at this relevance map, for example. The model is supposed to be looking at the bird, but most of its attention is scattered across the background grass. And sometimes, when the background changes, the model might fail. This leads to drastic performance drops on adversarial examples, unseen viewpoints, and artistic renditions. Prior work addresses spurious correlations by guiding the model toward foreground regions using binary segmentation masks. But binary masks are fundamentally coarse. They treat the entire object as a uniform region with no notion of which parts are actually discriminative. Consider recognizing a bird. What separates a lorikeet from a sparrow isn't a silhouette. It's the beak shape and the wing patterns. A foreground blob provides none of that signal. Look at the two masks on the right, for example. The coarse mask captures the scene broadly. The semantic mask precisely locates the parts that matter for the class. That gap in supervision quality is exactly what CFT closes, automatically, with no manual annotation required. Motivated by the recent success of concept bottleneck models in mitigating the robustness limitations of standard vision architectures, we investigate whether explicitly guiding a model to align with fine-grained interpretable semantic concepts can systematically improve its robustness. CFT operates in three stages. First, we use a language model to automatically generate a set of discriminative class-specific concepts. For a bird, that's things like beak, wings, feathers, and no manual annotation required. Second, we use grounded SEM, which combines grounding dinoid SEM to spatially localize these concepts in each training image, producing fine-grained semantic guidance masks automatically. Third, we fine-tune the model by aligning its internal relevance maps, computed via attention LRP, with these concept masks, while simultaneously suppressing attention to spurious background regions. The training objective has two complementary components. The concept promotion term drives the model's internal relevance into the validated concept regions, while the non-concept suppression term does the opposite. It actively penalizes any relevance assigned outside those regions, directly targeting the spurious background cues we want to eliminate. Together, those two terms amplify what matters and suppress what doesn't. The classification consistency loss then acts as a stabilizer, ensuring the model retains its predictive accuracy throughout the fine-tuning, preventing the explanation objective from collapsing the classifier. This objective aims to help the model learn meaningful fine-grained features and focus on them. CFT provides the most pronounced gains on the hardest challenges across all benchmarks, dataset with adversarial examples and control background changes where prior methods struggle the most. And crucially, the robustness improvements come without sacrificing in-distribution accuracy. The model doesn't forget what it learned, it just learns to reason better. This chart makes it easy to see. CFT consistently sits at the top across all baselines on ObjectNet. And I want to emphasize, these gains hold across all four architectures we tested, including one CNN architecture, and across all 5 out-of-distribution benchmarks. Beyond accuracy, CFT produces qualitatively better explanations. Relevance maps after CFT tightly focus on the semantically meaningful parts of the object, the beak and the body of the bird, the full form of the fish, rather than scattering across the background. Quantitatively, we measure a 10% improvement in mean IOU against human annotated ground truth masks. And importantly, these gains generalize to classes the model never saw in fine-tuning. This tells us CFT is genuinely refining the model's reasoning process, not just memorizing class-specific cues. To summarize, CFT is a scalable, fully automated framework that makes vision models more robust by teaching them to reason about the right things. Thank you for watching.